Hi guys, in this video we will continue with our look at the chemistry of acid derivatives. We have our outline here. We've covered this first page, and because my outline was not copied correctly, we were missing the back of the first page. And so I will pick up there, and essentially we are under Roman numeral 2, which is reactions of carboxylic acids. And the first reaction we saw was conversion of a carboxylic acid to an acid chloride using thionyl-chloride, the most common reagent for accomplishing this transformation. Next reaction of carboxylic acids is going to be conversion to esters. And the most common way by far is the Fischer esterification. All right, a couple of comments here that we will be referring to. A Fischer esterification involves reacting a carboxylic acid with an alcohol and H+ catalyst. And we essentially, we get an R group here, but it's important to note that this is not the same oxygen as here. And the best way to note that is this oxygen of the alcohol actually becomes this oxygen here. Okay? And I could say, well, the byproduct here is going to be water. I could say that this oxygen is lost as water, but actually during the mechanism these two oxygens become equivalent, and so it could be either one lost as water. So that's why I'm hesitant to star this one and say that one becomes water. But what is certain is this oxygen becomes the oxygen in your ester that's bonded to your R group. The OR bond is never broken in this reaction. Okay, that's a generic example. A precise example would be to take benzoic acid, react it with ethanol, and an acid catalyst. Now we typically use like sulfuric acid as an acid catalyst. All right, very often we've always used that, but that is an aqueous acid. And sometimes you would rather not have an aqueous acid, you'd rather use a dry acid. All right, we'll talk about why here. An alternative to an aqueous acid is para-toluene sulfonic acid. And that's going to be the toluene group. So I like tosyl chloride, okay? If this was a Cl, that would be tosyl chloride. This is tosyl OH. And it's para-toluene. Very often the P is omitted. Tosyl OH. And what we have here is a sulfonic acid. Now you would have the same ending in sulfuric acid, except over here you would have another OH. All right? But this is always aqueous. On the other hand, para-toluene sulfonic acid is a dry acid. Okay? It's actually a solid. But it is dry, or it can be dried and become anhydrous. So we have a strong acid without having any water. Now this is actually a true equilibrium reaction. Most of the reactions we do are highly favored towards products, and we never really ever talk about equilibrium. Here it's a genuine equilibrium reaction, and we need to talk about how to drive it to the right. One way to drive it to the right is to remove water as it's formed. Well, if you're looking to remove water, you don't want to add water when you add your acid catalyst. That's why you would want to use a dry acid. Okay. Let's look at the mechanism here. We're under acidic conditions. First thing you typically want to do is protonate something. We're going to protonate the carbonyl. We've talked about that. I'm just going to say phenyl here. Protonation of the carbonyl makes it more electrophilic. Now the weak nucleophile ethanol will attack this protonated carbonyl. Electrons up. We break the pi bond, right? That's going to give that there. Nucleophilic addition to protonated carbonyl. Now at this point we see that the two original oxygens are equivalent. We got two equivalent OH groups on the original carbonyl carbon. And at this point either one can be lost ultimately as that water, as I mentioned before. Okay, we need to lose one of the OHs and we want to keep the OR group. Well, right now the protonated oxygen is a better leaving group. Let's do a proton transfer. And that's going to give, all right, we can put the H on any oxygen. Why should this oxygen be protonated? Why not one of the others? They're just as basic or just as weakly basic. Okay. We've talked about proton transfers before. We don't need a mechanism error there. It's most likely intermolecular. Now we have this oxygen protonated. Now we can use these electrons, make pi bond, and kick off the better leaving group. That's going to give double bond to oxygen reformed. H is still there, positive charge, and O ethyl. Plus water, which we said we would be making. And now something can take the H to go to our final product. Well, what gave up the H? That would be the anion of, I'm just going to abbreviate that toluene group as kind of a phi, phenyl. These electrons take the H. These electrons move on to oxygen. And we get our product, plus we reform para-toluene sulfonic acid. Okay, every step here is reversible. That is, if you had this ester, couldn't you protonate it and get back to the protonated ester? And if you protonated the ester, couldn't you do a proton transfer and put the proton on the, I'm sorry, no, this would be water adding. A protonated ester, couldn't water add here? And to get to this tetrahedral intermediate? Yes. And at this point, couldn't you then do a proton transfer from this oxygen to this one? Okay, yes. And if this oxygen was protonated, couldn't you use one of the lone pairs from one of the oxygens to move in and make pi bond? To make carbonyl? Yes. And that would kick off the O ethyl, the protonated O ethyl. And if you got back to this point, couldn't something take this H and go back to the neutral carboxylic acid? Yes. Every step is completely reversible. It is a true equilibrium. We have to drive it one way or the other. To drive it towards product as shown, we could remove water as it's formed. That is the most common way. Actually, it's one of the most common ways. You can include a drying agent in the reaction to soak up the water as it's formed. You could theoretically boil the water out. The problem is, depends on the alcohol, because ethanol has a boiling point of about 78 degrees. If you tried to boil the water out as it's formed at 100 degrees, the boiling point of water, you would be boiling out your ethanol first, so that approach is not going to work. You can use like molecular sieves to soak up the water and remove it from the equilibrium. Another more common way to drive this equilibrium is to use excess of the alcohol. Okay? Excess. We can abbreviate that as XS. Because we can drive the equilibrium to the right by adding more of the starting materials. Where you don't want to add more of your acid, that is just theoretically not going to work. You want to consume all of your acid. You can use excess alcohol. Now you're only going to want to do that when the excess alcohol can be readily removed at the end of the reaction, such as on a rotovap. So small molecular weight alcohol such as methanol, ethanol, maybe isopropanol. Large alcohols you wouldn't want to use excess. Now, that is converting a carboxylic acid to an ester by a Fischer esterification. Fischer we've seen before, like Fischer projections. All right. Now the reverse, which we talked about, is also a reaction. The reverse would be taking an ester and converting it back to the carboxylic acid plus ethanol. That is just the reverse shown as a forward reaction. Now here you would be reacting this with what? The ester would react with water, but you would need acid, so it would be H3O plus, water and acid. And coming this way, since we're reacting with water, it would be a acid-catalyzed hydrolysis reaction. Now, of course, that was shown in the reaction diagram. Any derivative in the box, such as an ester, can be hydrolyzed back to the carboxylic acid using either acid and water, okay, H3O plus, which is what we just showed there. It's the reverse of a Fischer esterification. Or you could use aqueous base, okay? Now if you want to drive this to the right here, you would use excess water, okay? Of course you only need one drop of acid because catalyst, theoretically all you need is one molecule of the strong acid. But excess water will drive the equilibrium to the right. Or you could remove one of the products as it's formed. but the most common would be to use excess water if you want to go to the right. If you want to go from the acid to the ester, you could use excess alcohol. All right, so get that straight. Conversion to esters. Another way to make an ester, a little bit less common, but it's certainly very straightforward, is O-alkylation of a carboxylate anion. Now we actually showed this in Organic 1. If you take a carboxylic acid, react it with base, let's see, what kind of base would we use here? Maybe sodium hydroxide? These electrons take H, these electrons stay behind. We can just deprotonate our carboxylic acid and make the carboxylate anion. Now if we come in with an alkyl group with a leaving group, we can do SN2 and just alkylate the good nucleophile here. All right. Now in this case we are making the OR bond, where up here we did not ever make the OR bond. Up here we were doing carbonyl chemistry. The oxygen of the alcohol displaced ultimately water. Here we're not doing any chemistry at the carbonyl. We're deprotonating the carboxylic acid, making a strong or better nucleophile, and then just do a simple SN2 O-alkylation reaction. But we get the same product here. We get an ethyl ester by a different route. Okay, C. Well, A was conversion to acid chlorides, B was conversion to esters, C is conversion to acid anhydrides. Now we actually introduced anhydrides in the previous video because we sort of got ahead of ourselves. This is a mixed anhydride. It can be formed by reacting carboxylic acid with the base. Okay, same as above. I'm not going to show mechanism again. Just going to come to the carboxylate anion. Yeah. Well, instead of just alkylating it, we can actually acylate it. And these electrons attack here. Of course, we would not break the sigma bond, we break the weaker pi bond. When we react with the acid chloride, we get to this point here. Now the electrons can come back down and kick off the chlorine, and there you go. Plus Cl minus. Now there's a spectator ion here. I mean, the base has got to have maybe sodium hydroxide. Okay. If we go back up here, of course, we made that plus water. And then the sodium ion sits with that. And then ultimately we would also make here, if we use sodium hydroxide, you would make sodium iodide. All depends on what base you used here. If we use sodium hydroxide again, we would make water here and sodium chloride here. But you see, it's pretty straightforward chemistry. All right. We know we got a nucleophile, we know we have an acid chloride, this is the reaction we would expect, and yes, look at it, it's indeed a mixed anhydride. We have to think generally. Okay, so converting carboxylic acids to different functional groups. It looks like that's it. By the way, we did that over here. Carboxylic acid converted to acid chloride to esters, and we just converted it to a anhydride. There's actually another way to convert carboxylic acids to anhydrides, and it was shown in the previous video. That is by thermal or chemical dehydration, okay? Where, by the way, when we saw that, we said, we skipped one because we said C Roman numeral 2C. Well, Roman numeral 2C is what we just did. All right, please look at your headings to stay organized. Okay, then we would move to reactions of acid chlorides. We've already done this page. All right, and the next page, and we kind of left off at the previous video talking about this thermal dehydration to make, which is really only a good method for making symmetrical anhydrides. Okay. I think we may now be sort of back on track for this handout here. Next, let's look at cyclic anhydrides. Okay, now it's under this here. If you take a carboxylic acid and heat it up, you can get the anhydride and drive off water. All right, that's really a lot like a Fischer esterification, except the acid catalyst is sort of you'd have to assume that the weak acid, carboxylic acid, is sort of protonating its own carbonyl, or the carbonyl of another molecule. Because you typically do not need to add in an acid catalyst. But that's the way you want to do this mechanism. Basically, you can protonate one, and then the other starts reacting. Now again, we talked about this, probably this oxygen is more reactive. It reacts here, okay? And at this point, you keep doing what you need to do, and you can eventually eliminate the other OH group as water, okay, probably a proton transfer, and you can work your way towards this structure and elimination of water. All right. Now the thermal dehydration really works well with diacids. Okay, instead of two separate carboxylic acids, okay, identical but two separate molecules. If you take a diacid, which is one molecule but contains two carboxylic acids within it, these are readily dehydrated upon heating because the internal reaction is so much faster. And you see these cyclic anhydrides very often. Okay? You should kind of see here one of the oxygens end up binding to the other carbonyl, and you split out water. Make sure you see what's going on here. You may remember in Organic 1 we used, for those who took me, we used this anhydride, which is similar to succinic anhydride, but it has the alkene here, and it's called maleic anhydride. And we use that as a dienophile for a Diels-Alder reaction. And if you take succinic acid and just have a double bond here, it's called maleic acid. All right. Okay, now what about reactions of anhydrides? Well, they react a lot like acid chlorides, but they're not quite as reactive. All right, they sit a little bit lower here. What we also have to understand is you typically attack one carbonyl, and the oxygen and the remainder, the other carbonyl, all that serves as the leaving group from one carbonyl. Now, if your anhydride is symmetrical, it doesn't matter which carbonyl you attack. If it is a mixed anhydride, you will have to decide which carbonyl is most reactive. But with acetic anhydride, you don't have to make that choice. They're identical. Okay? Or any other symmetrical anhydride. So the nucleophile attacks carbonyl, electrons up. Okay? That's going to give something like this. Now we may have a proton here to take care of, but in my generic scheme here I do not. Now these electrons can come back down and kick off this oxygen. That will give this product, a nucleophile now bonded to your carbonyl, but the leaving group was actually a carboxylate anion. Okay, so resin is stabilized, and so it is a pretty good Lg. Of course, Lg ability is not really important because this is a fast step, but still we can consider leaving group ability. We talked about the reactivity of anhydrides. Okay. All right. Now, anhydrides have, they're not as commonly used as acid chlorides. One reason is because you lose, your leaving group is so big, and when you make the anhydride, you know, you need two carbonyl components. And so it's just not that really efficient in terms of atom efficiency. I'm not going to take time to explain that much further. Although we do kind of explain that here. And let's look at that. Okay. Basically, if you do this reaction, this is your leaving group. This is going to end up in the waste container, okay? Usually. Now you could recycle it, but that takes effort. And ultimately, you don't want to be sort of wasting organic components here. It's much better to put just chloride ions into the waste container. But let's look at this. Let's say you had 1 mole of a carboxylic acid, and you wanted to convert it to something that reacted better with nucleophiles, such as the acid chloride. Well, 1 mole of this becomes 1 mole of this. On the other hand, if you take 1 mole of a carboxylic acid and do a thermal dehydration, you're only going to get a half a mole of the anhydride. Or you could say this is, you need 2 moles here, and 2 moles of that would give 1 mole here. But another way to say that is say 1 here and a half a mole here. All right. Now, if here you could come in here and react with maybe ammonia, displace the chlorine, and get an amide, but 1 mole of this would give 1 mole of this. All right. Down here, you could also react this with ammonia. And like we said, it'd come in here and you would attack this carbonyl. The other carbonyl portion would be your leaving group. All right. And so this would go into the waste container. So ultimately, in both cases, we started with 1 mole of a carboxylic acid. If we proceed via the acid chloride, we can get 1 mole of amide. But if you proceed via the anhydride, you're only going to get a half a mole of amide. Now, if you spent maybe a year making some very complex carboxylic acid, you don't want to eventually put half of it in the waste container. Or maybe you bought this carboxylic acid, but maybe it was $100 a gram. You'd be putting a lot of money into the waste container, or you'd have to spend a lot of time recycling this, okay, back to the carboxylic acid. The route going via the acid chloride, you have much better atom economy. And that's one of the main reasons that acid chlorides are preferred. They're also more reactive, all right? But there are some special cases where you would use an anhydride. And one case is acid chlorides, again, tend to be unstable. Okay? We talked about how they react with moisture in the air. All right? They may be hard to store. Where an anhydride, because it's a little less reactive, they typically don't react with moisture in the air, and they can be stored longer. But they're still reactive enough to be pretty easy to do chemistry with. If the anhydride can be bought and it's cheap, then it's a good option. And one cheap one is acetic anhydride. Remember, you can buy a gallon of it pretty darn cheap. All right. So here's some to do for homework. All right. We have a cyclic anhydride. Here the anhydride is on the arrow. Here is the starting material on the left. Okay. Show products there. We can also look at mixed anhydrides. All right. It's kind of a little bit of both here. Another reason you might use an anhydride is this acid chloride is actually not stable. Okay, so it just cannot be made and stored. But the anhydride is stable. And in both cases, you're attacking a carbonyl, and this would be your leaving group, okay, instead of the chlorine. So that's a case where you just cannot use the acid chloride. Here, this acid chloride is also not stable. It's the acid chloride of formic acid. If you try to take formic acid and react it with thionyl chloride to get this acid chloride, you're just not going to get this product. It's not stable. I'm not going to take time to maybe explain that. But this mixed anhydride is stable. And this is the leaving group. And we see we have the same carbonyl there other than the leaving group. All right. Now I showed this mixed anhydride here. Now the question is, this is your nucleophile. Which carbonyl are we going to attack? And it turns out that the nucleophiles preferentially attack the carbonyl on the left because the one on the right has a donating sp3 carbon. And any partial plus here is somewhat quenched by this donation. All right. So we have electron donation. That's an electronic effect. We also have a steric effect because the methyl group is substantially larger than just the H. So it turns out that we attack this carbonyl here, and the other portion serves as the leaving group. I've used this mixed anhydride before, and it reacts very preferentially at this carbonyl. So also try these for homework. This down here is not exactly an anhydride because there's an oxygen on the left here as well. Think about which carbonyl we would attack here. Try to show a product here. Of course, TEA is triethylamine. All right. We showed that back over when we were talking about reactions of amines with acid chlorides. You really need to look through this and come up with your own questions. Let's end here with a biochemical application. This is phosphoric acid. If you heat it, you can also do a thermal dehydration and get an anhydride. Okay, you can make this sort of dimerize and lose water. The oxygen is now bonded to 2 phosphorus groups, analogous to a carboxylic acid anhydride. This is called pyrophosphoric acid. The pyro kind of comes from high heating. It's a term that means like pyrolysis, high heating. Now you still have some OH groups remaining here, and with base they can become anions, okay? And lots of anions. But this molecule is called pyrophosphate, and it's actually seen in biochemistry. It's the tetraanion of this, and this is an anhydride of phosphoric acid. All right. We're not really going to do anything chemistry here, but I just wanted you to see an analogous acid anhydride. All right. We'll end there. We'll pick up in the next video with chemistry of esters. We've actually already seen ways to make esters in this video here. All right. So we'll pick up there. Chemistry of esters, how to make them, what reactions you can do. Then we'll move to chemistries of amides and chemistry of nitriles. All right. There's also some applications here, including some polymers. Take a look. Okay, guys.